In the past, we have found the derivative of a function using the first principles of derivatives, which involve limits. Now, that was a tedious process. It was good for functions that were on the more basic side. So now it's time to learn some derivative shortcuts to make things faster and to build up the skills so that we can find the derivative of more complicated functions. So we're going to start with the constant function rule, and it just says if your function is a constant k, then the derivative is just equal to 0. And remember, the derivative represents the slope of a tangent line. So if my function is f at x equals 2, that's just a horizontal line going through 2. This is the function, y equals 2. And the slope at every single point on that line is 0. And the line itself is actually the tangent line as well. So f prime of x is 0. If my function is pi is just a number, it's not a variable. So the derivative of g of x is 0. If I have this function y equals -3, the square root of x times the cube root of x to the 5, all to the power of 0, if we remember our exponent rules, anything to the power of 0 is actually equal to 1. So this function is actually just a horizontal line going through 1, which means the derivative, y prime, is 0. Now we can write this derivative as y prime, or we could write it as dy dx equals 0. So that's just saying I'm taking the derivative of y in terms of x, and that derivative is 0. Next, we have the power rule, and that's if I have x to the power of any real number, so x to the power of n, then the derivative is bring the exponent down, write your variable, and then it's going to be to the power of 1 less than the original exponent. So if I have f at x is equal to x squared, f prime of x is going to be bring the 2 down, and 2 minus 1 is 1. Now I would just write it as 2x, but just to show that I subtracted 1, there it is. If I have x to the 5, the derivative is bring the 5 down, and now it's x to the 4 because I subtracted 1. Next, h of x equals x to the -4. The derivative, I'm going to bring the exponent down, which is negative, and just be careful here. When I subtract 1 from a negative number, I'm making it more negative. So -4 minus 1 is -5. Now, if I wanted to take this a little bit of a step further here, typically we don't like the negative exponents. So I'm just going to bring that negative exponent down into the denominator. So I'm taking a reciprocal of that base to make the exponent positive. And now when I see a variable in the denominator, I'm thinking, oh, this is a rational function. I should have a restriction. And that restriction is that x cannot equal 0. Otherwise, we'll have to divide by 0, which we know we cannot do. Now let's move on to the constant multiple rule. And that just says if I have a constant in front of a function, then I just take the derivative of the function and the constant just stays there. It doesn't affect it. So if I have k, where k is the constant times g of x, k will stay, and I'll just take the derivative of that function. And right now we have the power rule, so let's apply this to the power rule. I have f at x is equal to 2 times x to the 6. We can treat x to the 6 as that new function. So the derivative, the 2 relaxes. I'm just going to put in brackets just to show the point. The derivative of x to the 6 is 6 times x to the 5. And this can, of course, be cleaned up. 2 times 6 is 12. And we are going to be more efficient. We're not going to do this in 2 steps. Just if I have a constant in front of my variable, when I bring that exponent down, I'm just going to multiply it with the constant just to speed things up. And as we get more efficient, this will be ideal. Okay. So for the next one, I bring the exponent of 4 down. That 4 will get multiplied by -3. So now I have -12. X to the power of 4 minus 1 is 3. Done. The next one, I have a rational exponent. Remember, rational exponents represent some type of root. So an exponent of a half actually means the square root of x, so 2 times the square root of x. But seeing the rational exponent is more helpful in terms of derivatives. So when I take the derivative, whether I write y prime or I write dy dx, both work. I'm going to do 2 times a half, which is 1, so I'm not going to write that. And then x to the power of a half minus 1 is negative a half. Remember, you just need a common denominator. So a half minus 1 is really a half minus 2 over 2, and there we are. And now again, I'm going to take this a step further. I don't want that negative exponent, so I'm going to bring it down into the denominator. So I'm going to have 1 over x to the power of a half, but I'm also going to bring the root back in. So instead of x to the power of a half, I'm going to write the square root of x. And now again, I know I have a restriction here because my denominator can't be 0, meaning x cannot be 0. But also, I have a radical here and I can't take the square root of a negative number. So x also has to be greater than 0. Now, typically with a square root, I can square root a 0, but because it's in the denominator, I can't have a 0 in the denominator. So my restriction is that x must be greater than 0. And final rule for today, if I have a function that is made up of the sum or difference of other functions, I'm just taking the derivative of the individual function. So if I have p of x plus or minus q of x, the derivative is just p prime of x plus or minus whatever the operation was, q prime of x. So again, using our power rule and applying it to the sum and difference rule, here I have a function, it's just a cubic function, this f at x. I'm going to take the derivative of the individual pieces, and that will be the derivative of the entire function. So the derivative of x cubed is 3x squared. The derivative of negative 4x squared is negative 8x. That 2 comes down, multiplies with the negative 4. There we are. The derivative of 5x, remember, there's technically an invisible exponent of 1, so 5 times 1 is 5, and then it would be x to the power of 0, but anything to the power of 0 is 1, so, and 5 times 1 is 5, so I'm not going to write that. And then the derivative of a constant is 0, so I'm not going to write that either. There we are. We started with the cubic function, the derivative is quadratic. For the next one, I could write y prime, or I could write dy dx, and bring the 8 down, so negative 8, x to the 7. Bring the 6 down, 3 times 6 is 18, x to the 5. Bring the 2 down, so we have negative 16x, and plus 5. Okay, again, started with power of 8, went down to power of 7. And the final one, we have a negative exponent in there, so we might have to do a little bit more in terms of the cleaning up, but here we go. Bring the 3 down, so we have 3 times a half is 3 over 2, and then x squared. Bring the negative 2 down, it's now subtract 2x, and x will be to the power of negative 3. Now I'm going to take that exponent or that variable, bring it down into the denominator. I'm going to make these look more like fractions, so 3x squared over 2, subtract 2 over x cubed. When I say 2 separate fractions, I'm thinking, oh, I should get a common denominator to unite this. So I'm going to multiply that first fraction by x cubed and the second one by 2, so that I have this common denominator of 2x cubed. So I'm going to have 3x to the 5, top and bottom get multiplied by x cubed, and the second one times 2, negative 2 times 2 is negative 4. There's my function. This would be ideal if I wanted to graph it or do something with this later on, solving wise. And now my restriction, x cannot be 0 because of that denominator. So there are our derivative rules. They're foundational rules here, and they make things so much faster. Imagine having to do first principles on a polynomial that was to the power of 8. That would not be fun at all. So let's move on. Make them a little fancier we might have to modify some of these functions so that they're more usable with our rules. Later on, we'll learn some more efficient methods for more complicated functions, but for now, we're going to use what we know, and we're going to make sure our final answer has positive exponents, and we're going to include any restrictions if they apply. So I'm going to start with y equals the 4th root of x. The first thing I'm going to do is rewrite this as x to the power of a quarter. Now I can use my power rule. So bring the 1/4 down, and x is now to the power of a quarter minus 1, which is -3/4. Okay, now I'm going to bring the variable down into the denominator with the 4, while I also fix up that exponent, that rational exponent. So I'm going to have 1/4. Remember, the denominator of your fraction tells you the type of root, so I'm going to take the 4th root of x cubed. And there we are. And then my restriction here, because it is an even root, I do know that I'm going to have to write it as x is greater than 0, because I cannot take the 4th root or the even root of a negative number. Now, if I wanted to take this a step further, because typically we don't like radicals in the denominator, I can. And for this, I'm actually going to go back to x to the power of 3/4. And then I think to myself, okay, what should I multiply x to the power of 3/4 by so that the fraction's gone? And if I multiplied it by x to the power of a quarter, 3/4 times a quarter is 4/4, which is 1, and then boom, I don't have a radical in the denominator anymore. And whatever I do to the bottom, I do to the top. So I could also rewrite this as the 4th root of x over 4x. So if we wanted to take it a little further. All right, y equals 1/x². Now we don't know a rule for when we have the division of two functions. And we'll learn it later on, but right now we don't know it. But this can easily be turned into x to the power of -2. And now I can take the derivative. Bring the -2 down, subtract 1 from the exponent, and I want positive exponents, so I'm going to bring the x cubed into the denominator. And here, x cannot be 0. Likewise, for the next one, just be careful here. I'm going to bring the x to the 5 up into the numerator, making the exponent negative. The 3 does not move with it, so the coefficient is -1/3, and then x to the -5. And the derivative, bring the -5 down. Two negatives make a positive, 5/3, and x to the -6. Clean it up. X to the 6 comes down, and I can see x cannot be 0. Now, the next one, I have a bracket to the power of 2, and again, we're going to have a rule of how to find this derivative, but we don't know it yet. So I'm going to have to expand and simplify this. So 2x minus 3 times 2x minus 3 is 4x² minus 6x minus 6x again, so minus 12x plus 9. And now I'll take the derivative, because this is just a nice little power rule. 8x minus 12. All right, the next one. Just before I take the derivative, I'm going to write the square root of x as x to the power of a half. And now off we go. Bring the 4 down. We have 8x cubed. Bring the 1/2. We have 2 x to the power of -1/2. And the derivative of 7 is 0. Going to clean this up. Okay, and I'm having two problems here. I have a fraction and I have a radical in the denominator. So I'm going to do a little bit more cleaning up. I'm going to multiply this one by root x, which makes the denominator now x. And I'm going to multiply the first fraction by x just to get a common denominator. So I'm going to have 8x to the 4 minus 2 root x all over x. And here my restriction, x can't be 0 because of the denominator, but because of the radical as well, I'm actually going to change this to x has to be greater than 0. Next one, I'm going to clean this up to 4x to the negative 5 minus 3x squared plus 6x to the negative 1. And now I'll take the derivative. Negative 20x to the negative 6, just be careful with those negative exponents, minus 6x, subtract 6x to the negative 2. Okay, and now we'll bring them down into the denominator, get a common denominator, and write our restriction. So for this, we're doing our rule, but then there's a little bit more cleaning up than with those original basics from the rules. So we have negative 20 over x to the 6 minus 6x minus 6x squared. And the reason we will need our cleaning up skills, just simplifying algebra skills, that kind of thing, is for when we have to do more with this derivative. Maybe we have to set the derivative equal to a number and solve for x, and we would like the cleaned up version to do that. So here my common denominator will be x to the 6. The first one's fine. The second one, which is over 1, is going to have to get multiplied by x to the 6, which makes it negative 6x to the 7. And the last one has to get multiplied by x to the 4 to get to that x to the 6. And my restriction, x can't be 0. All right, 2 more before we get into some typical derivative questions. We've seen them in the past, but now they can be a little bit more complicated because of these rules. Okay, clean things up first. 3x to the power of a half plus 16x cubed all to the power of 1/4. And actually 16 to the power of a quarter, or the 4th root of 16, is 2, so I'm going to clean this up a little bit more and write it as 2x to the power of 3/4. So actually applying that 4th root in. All right. Bring the 1/2 down, and we have 3 over 2x to the power of negative a half. Bring the 3/4 down, and we have 2 times 3/4 is 6 over 4, which is 3 over 2. And then x to the power of negative a quarter. Negative exponents, let's deal with those. Actually, you know what? For this one, I'm going to keep it as a quarter because I don't want any radicals in the denominator. Just if I'm taking that extra step. So the first fraction, I'm going to multiply top and bottom by root x. The next one by x to the power of 3/4. That way, a quarter plus 3/4 is 1, and the radical is gone. And while I did that, I also just got a common denominator of 2x. So that's fantastic for us there. 3 root x plus 3 times the 4th root of x cubed. And here we want x to be greater than 0 and not equal to 0 because of the denominator. All right, one more. P of x is equal to this rational function. Now, again, we don't know this quotient rule that we're going to learn later on for how to take the derivative when we have two functions being divided. So I'm going to try to simplify this rational function by factoring. The numerator has a nice GCF. Now, normally I would take out 2x cubed, but I really just need the denominator to disappear, so I'm only going to take out 2x squared, so that I'm left with x to the 3 minus 8x all over 2x squared, and then these go away. And now our derivative is 3x squared minus 8. All right, let's move on to some typical derivative questions. Determine the equation of the tangent to the graph of y equals x squared plus 1 times x minus 3 at the point where x equals 1. we've done these in the past. First thing I'm going to do though, I'm going to expand this function so that I can use my derivative rules. So x cubed minus 3x squared plus x minus 3. Now I'm going to find the derivative. I know the derivative represents the slope of the tangent, so that's going to help me find m in y equals mx plus b. The derivative is 3x squared minus 6x plus 1. So now I need to know what the derivative is of that tangent line when x is 1. So I'm going to set x equal to 1 here. So the only new part of this question is using our nice rules to speed things up. So we're going to have 3 minus 6 plus 1 is negative 2 for our slope. That's going to be helpful. Now I know my equation is y equals negative 2x plus b, but of course we need a point to sub in. So I'm also going to sub 1 into the original function as well. 1 squared plus 1, 1 minus 3, and the coordinate itself is 1, negative 4. Now we can sub that in to find the y-intercept of the tangent line. Negative 2 times 1 is negative 2, and when we bring it over, it'll be positive. So the y-intercept is negative 2. And here's the equation of the tangent line when x is equal to 1. We've done these questions in the past, but now took up less space and was much faster, and we did it on a more complicated function that we wouldn't have really done using first principles. All right, let's go to the next one. Determine the points on the graph of m at x where the tangent lines are horizontal. If I want horizontal tangent lines, I need the slope to be 0. And the slope of the tangent line is the derivative of the function. So I need to find the derivative of this function, set it equal to 0, and solve for x. And our derivative will be much faster here. And feel free to pause the video and try the question on your own, and then come back to check. There's my derivative, constantly bringing the exponents down and dropping each exponent by 1. And now I'm not going to set x equal to anything because I'm trying to find those x values when the slope of the tangent line is specifically 0. And now we're in grade 10. We can either solve this by factoring or a quadratic formula. This does look factorable though, so let's give it a try. 3x, 1x adds up to 4x, so that's fantastic. And here are the factor brackets. Branch out because we are trying to solve for x. X is equal to negative 1/3 from the first one and negative 1 from the second. So those are the x values. I am asked for the points, so the coordinates themselves, so I'll just do that extra little step here. Let's find m at negative 1. So because I'm actually finding a point on the function, I'm going to m at x, not its derivative. So negative 1 cubed plus 2 times negative 1 squared plus negative 1 minus 5. We could punch that into our calculators or do mental math and get negative 5. M to the negative 1/3. Gonna do the same thing. And if I want to keep this in exact form, I'm not going to go to my calculator. I'm going to use my fraction knowledge here. So negative 1/3 to the power of 3 is negative 1 over 27. Remember that exponent is just applying to top and bottom. Plus negative 1/3 to the power of 2 is 1 over 9 times 2 is 2 over 9 minus 1/3 minus, I'm just going to write 5 over 1. And then I'll just get a common denominator so I can add and subtract these fractions. So 27 is the goal. 9 times 3, so 2 times 3 is 6. 3 times 9, negative 1 times 9 is negative 9. And negative 5 times 27, negative 135. And now we can punch this in or evaluate our numerators, and we get negative 139 over 27 for the coordinate. So there we are, at negative 1, negative 5, and at negative a third, comma, negative 139 over 27, the tangent lines are horizontal. And when are the tangent lines horizontal? When our function is potentially changing directions. So maybe we have a minimum, or maybe we have a maximum, and that's where those tangent lines are horizontal. All right. For what value or values of x are the tangent lines to the graph of f at x equals that quadratic and g of x equals that cubic parallel? So if we want our tangent lines to be parallel, that means the slope of the tangent lines should be the same. And if the slope of the tangent lines are the same, that means the derivatives are the same. So we are trying to find when is f prime of x equal to g prime of x. So let's do it. The derivative of f at x is 4x minus 4. And the derivative of g of x, a third times 3 is 1. And then x squared plus 8x minus 25. There it is. Now I have a quadratic equation, so I'm going to bring everything over to one side. 8x minus 4x is 4x, and negative 25 plus 4 is negative 21. This factor is nice. X times x, 7 times negative 3, 7x and negative 3x does add up to 4x, so here we are. Which means when x is negative 7 and when x is positive 3, the tangent lines of these graphs are parallel. And final question here, a little word problem, bringing back some A-rock, I-rock. A stone falls freely from rest from the edge of a cliff. After t seconds, its height with respect to the cliff is h at t equals negative 5t squared in meters. What does the derivative of h of t represent? Well, if we're doing the change in height, so change in height over change in time, that's our slope, but that is just velocity. Now, the reason it's not just speed but also velocity is because depending on the sign of this rate of change, we'll know if the stone is going upwards or downwards. And because it's falling, we are expecting it to be going down. And now for B, find the average rate of change, the average velocity of the stone between 2 seconds and 4.5 seconds. So B is average rate of change, which means we're just using our slope formula. Find h at t, find h at 4.5, and do good old y2 minus y1, x2 minus x1. So h at 2, if we punch it in, 2 squared is 4 times negative 5 is negative 20. And for 4.5, plug it in, and we get negative 101.25. Now, these heights are negative because negative here is going to apply we are below the cliff while this stone is falling. And now for my average rate of change, y2 minus y1 over x2 minus x1. Just gonna punch it into my calculator, and I get negative 32.5, and my units here, we're talking about meters and second, so negative 32.5 meters per second. And and I would add a therefore statement here, so therefore the average velocity between 2 and 4.5 seconds is negative 32.5 meters per second. C C, we're being asked for the instantaneous velocity at 2 seconds. That means we're looking for our IROC. Now, in the past, we did this with, first principles, or in advanced functions, we found a point very close to the right and to the left, but now we have our quick derivative shortcuts. So if I'm asked for the instantaneous velocity, I'm just being asked for the derivative of the height at 2 seconds. So let's find the derivative. It's going to be negative 10t, and now we can replace t with 2. So much faster. So negative 2 meters per second. Therefore, the instantaneous velocity at 2 seconds is negative 20 meters per second. So now we've learned all of these foundational and basic derivative rules to speed things up when we're finding the derivative. They allow us to find the derivatives of more complicated functions, and they allow us to solve these types of word problems, application problems faster, because the derivative will come much quicker to us, and then we can just focus on solving an equation or finding an equation of a tangent line, that kind of thing.